All right, let's step into the shoes of a digital detective. Today, we're going to break down what happens when tech becomes a key part of a crime scene. How do investigators pull that critical evidence out of a computer without, completely destroying it? So let's grab our digital toolkit and get right into it.
So, picture this. You arrive on scene, and there it is. A laptop just sitting there, open and humming. Every single move you make from this point on is absolutely critical. One wrong click, one bad decision, and that crucial piece of evidence could just vanish forever. It could even be thrown out of court. So what's the first, most important choice you have to make?
Well, it all comes down to one simple question. Is the power on or off? Seriously, this one thing dictates your entire strategy. If it's on, you're in a race against time. You got to perform what's called a live acquisition to grab data that's changing by the second. But if it's off, your mission is totally different. Now you have to do a dead acquisition and create a perfect, untainted clone of that hard drive. Two very different paths, two completely different sets of challenges.
Okay, so let's go down that first path. The machine is on. Right now, we're dealing with what investigators call volatile data. These are like digital ghosts that will disappear the second you pull the plug. The hunt is officially on.
Think of volatile data kind of like the computer's short-term memory. It's everything that's happening right now. The programs that are running, open network connections, any unsaved documents. All of this information lives in the computer's RAM and cache, and it is incredibly fragile. The moment you power down that system, poof, it's gone forever. And this is often where you find the real smoking gun.
So how in the world do you capture all of that before it just vanishes? Well, to do that, investigators have to follow this super strict triage plan. It's called the order of volatility. They start with the most fragile data first and then work their way down to the most stable. So registers and cache are up first because they're tied to what the CPU is doing, like right this nanosecond. Then comes the RAM, which is the system's active workspace. It's just a methodical sprint to preserve every single last bit.
But what if you show up and the computer's already off? The pressure is different, but believe me, the stakes are just as high. Now the mission completely changes. You need to create a perfect, and I mean perfect, replica of that evidence drive.
So here's the fundamental challenge, right? The second you plug a hard drive into a regular computer, the operating system immediately tries to talk to it, maybe write some new data, or just alter timestamps. And just like that, you've contaminated the evidence. So how do you look at all that data without changing a single solitary bit?
You use this brilliant little piece of hardware, a write blocker. It's basically a one-way street for data. A write blocker lets an investigator read all the information from a drive, but it physically stops any command to write, change, or delete anything. It's the absolute golden key to making sure that original evidence stays pristine.
Now with that write blocker safely in place, the investigator creates what's known as a bit stream image. And listen, this is not your standard drag-and-drop file copy. Oh no, a bitstream image is a perfect bit-for-bit clone of the entire drive. Every file, every deleted fragment, every single hidden corner of that disk. The analysis is always done on this clone, leaving the original evidence totally untouched.
Okay, so you've made a perfect clone. But in a court of law, you can't just say it's perfect. You have to prove it. So how do you do that? You need a way to verify, with math, that your copy and the original are identical. You need what's called a digital fingerprint.
Really think about it. We could be talking about terabytes of data. How can you be absolutely 100% certain that not a single 0 or 1 has been flipped out of place between that original drive and your forensic copy? The answer is something called a hash value. The easiest way to think of it is like a unique barcode for data. A hashing algorithm, you might have heard of MD5 or SHA-256. It runs this really complex math function on a piece of data and then spits out a unique string of letters and numbers. And its real power is in its sensitivity. If you change even one single bit in the original data, like just one tiny comma in a 1,000-page document, the hash value that comes out will be completely different. It really is a digital fingerprint.
So here's the crucial part. An investigator calculates the hash value for the original suspect drive. Then, after they make that bitstream image, they calculate the hash value for the new image file. And as you can see right here, if those two long strings are identical, that is mathematical proof that the copy is perfect and the evidence is untainted. Boom, integrity verified.
Now, all these cool technical steps, they don't just happen in a vacuum. They're all part of a super strict, legally defensible process. This is the investigator's playbook, and it's governed by rules that make sure every piece of evidence can stand up to scrutiny in court.
And these are the non-negotiables. You have to document everything. You never, ever work on the original evidence. You always create and verify a duplicate. And critically, you have to maintain a secure chain of custody. That's a detailed log of every single person who has handled the evidence, from the moment it's found to the moment it's in the courtroom. If you break this chain, the evidence gets thrown out. Simple as that.
All of this detective work we've been talking about is really just the first step in a much larger legal framework called e-discovery. It's basically the official rulebook for handling any kind of digital evidence, what lawyers call electronically stored information, or ESI, from the crime scene all the way to the courthouse steps. This model here, the Electronic Discovery Reference Model, it shows you the whole life cycle. Our digital detective starts right here, at identification, preservation, and collection. From there, that cloned data gets processed, reviewed by legal teams, analyzed for context, and then, finally, it's presented in court. It is a long, long road from the crime scene to the courtroom.
So, we've seen how investigators have to meticulously preserve and clone digital evidence, but the challenges, they're constantly changing. I mean, with crazy encryption, data scattered all over the cloud, and now the rise of AI-generated deepfakes, the digital detective's job is only getting harder. The principles we talked about, they're still the same, but the methods are going to have to constantly adapt just to keep up. Which leaves us with the big question. What's the next playbook going to look like?